All right, thank you. So sperm whales. I want to talk today about AI and how it can help us discover new patterns in data. So we have a pretty good understanding of the world around us, but there's, of course, obviously, there's still many things to be discovered. And for the first time, maybe in history, the AI has become so good that it can actually give us insight into new discoveries and help us find it. So it can be a tool to find new properties in data, and all sorts of data, from protein to mathematics, geometry, and I'm going to talk about the animal communication. So it's a one of the focuses of my lab is to try to understand how AI learns and how it learns things internally. And that can give us a really important causal insights into data that I'm going to talk about today. And this is an exciting time because we have animals and humans, and we've been talking about animals and humans for very long, and now we have AI, and I think there are two sides of the same debate that are playing out right now. One is, are humans just smarter animals, and the other, and as you increase animal brain size and potential, language happens and whatever material culture, and the other is, as we're going to increase power in AI, will that emerge and happen as well? Okay, so that's just to think about. So it is very important that we try to understand how artificial intelligence learns, because we can build models of human language and understand how we're similar and different, how our artificial neural computation is similar and different from biological neural computation. And we will be able, we are able to better understand what is uniquely human about language, if anything, and how language emerges and how that happens. And we can use AI models again to our advantage to help us find insights into various data. So humans are biased, right? We as researchers are biased. We see things, sometimes we only hear certain frequencies. And we observe things that are important to us. And that can prevent us from observing patterns that are there. And so AI can help there because it is, in a sense, less biased, right? It can hear more things. It can observe, it can process different types of information. And it's performing well on many tasks. We just don't understand very well how. And I think that can be changed. Okay, so how do we discover meaning in unknown data? I think we're all here in this room for this precise reason. How you have some data, you have some communication system you don't know anything about. How do you get meaning from that? And I'm going to talk about sperm whale communication system. And a case study where our AI interpretability technique predicted something that we didn't know before. And then we went and checked, and the pattern appeared there. And this is a nice case where basically AI helped us get an insight into something that we called sperm whale vowels, which is, we found that sperm whales have an analogs to how we produce vowels in human language. To do that, we first had to work with language. Okay, I'm a linguist, so my main objective of study is human language. And we have LLMs now, which are great, but they don't learn language like humans do. No baby learns language from text. No baby learns language from massive amounts of text. No baby learns language without hearing and speaking. No baby learns without having communicative intent. So how do we learn language? I have some information in my brain. I move my muscles so that produces sounds. I send air through my lungs, of course. And you hear those vibrations. That vibrations in your ear get into your electric signal into your brain, and you decode it. And hopefully my information is the same as your information. That's how it happens. And I also incidentally hear myself as well. So there's this loop where I hear myself speaking as well. So we're building the most realistic model of human language learning using deep learning that I know so far. Which has a lot of properties of language baked in, okay? So we have information exchange. So we have two networks that need to learn to encode and decode. These are based on GANs, or generative adversarial networks, which is a fabulous architecture. We have a model that is not just producing sound, but is actually moving articulators, moving sound, mouth and tongue and jaws, so that the sound that it's hearing approximates what it hears from the parent. And we have a network that forces imitation. Okay, this is learning by imitation. And we were able to show that lots of things in language are learned in this way. The model is, there's nothing that forces the model to learn language, yet it learns words, it learns morphophonological processes, it learns meaning, and so on and so on. So we have a model that is doing well on language, okay? So it's performing pretty well. And even show that internally, if you compare these are convolutional neural networks, which are much more biologically similar to our brain than transformers, for example. And we've shown that we even process neurally sounds similarly compared to these models. And this is a syllable that was played to many participants, and you can hear that it sounds similarly in the brain and in artificial neural networks. This is the brain. This is artificial neural networks. Okay, that's humans. Okay, we have a good model roughly of human language with deep neural nets. We basically take our artificial baby language learner and ask it learn Walish. Okay. Now our model's crucial thing is that it learns by imitation. That is so important. Other architectures were mentioned. Autoencoders learn by replicating data. The GANs learn by imitation, and that is super important. Okay. So if you think of whales, maybe they have the same kind of process. Maybe they encode information into codas, a set of clicks that are called codas, and then they decode it. Now, the cool thing about this communication system, the reason why we think it's meaningful, is that it happens before hunting, it happens while they're socializing, and so, but we still don't know what they're conveying. But it appears very strong. It appears that there's some referential meaning there. So we have a project called Project CETI, where we collect the data and we bring together, people from all sorts of backgrounds, and we have a station in Dominica, and we place tags on whales, and those tags record whales. And these whales are not easy to track because they dive up to 1 kilometer deep. They need the open sea. And so we have several sets of data collection devices. And this is how roughly they look like. Okay, before they hunt, they exchange this set of clicks that are called codas in conversations. Whale to whale. Click, 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 click. That's a pretty common one. It's so beautiful. Okay, so they're talking about they're socializing and before they hunt. As I mentioned, they have clicks, set of clicks that I group into codas, and they have sets of codas that exchange in conversations. Okay, so this is one coda, this is another coda, and so traditionally they have been classified into coda types. Okay, traditionally this system was considered a Morse code, essentially. Number of clicks matters and timing between them. Okay. And this is how they represented it. The various different click types. For example, you have a click type, a coda type, 5 clicks. Click, 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 click. You have another coda type, 1 plus 1 plus 3. Click, 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 click. Okay. So how do we approach something? What is meaningful in this communication system? We still don't know. Okay. So what we did is we took our artificial baby language learner that performed really well on language. It learned language super well. And we asked him learn whales and learn to encode information into those codas. So what our artificial neural network needs to do, it needs to imitate whales, and it needs to encode unique information into those imitations. Now, what we do is we use our interpretability technique that we've developed for language to understand what kinds of acoustic properties did our artificial neural network use in order to exchange information. Okay? So we're trying to look inside the neural net and ask it, what did you do in order to convey information through codas, through sperm wave clicks? And we have this interpretability technique that very effectively tells you what each individual neuron is encoding. And we borrow from causal inference methods in statistics, methods to show that individual bits encode meaningful properties about the communication system. And that's all emergent. That's all emergent by two requirements: imitate and imitate informatively. Okay? So, as I mentioned, this was considered to be a Morse code, but our AI model suggested otherwise. It suggested that there's more than just timing and number of clicks. So our model suggested that spectral properties are also informative. Okay, and so then we went and checked. And we found this equivalent to human vowels. But the crucial step that we need to make here is their timing works differently. Time in sperm whales, I think, is just different. And that was crucial for us to get to the final answer. So their heartbeat is only 15 times per minute. And I think in general, they have a slower life, slower world around them. So when I say my vowels, okay, this is me saying ah and e.
E.
A recording of myself, probably hear it. What happens is, as in ah, I open my jaw very low, and in e, it's a little bit more close, okay? So ah versus e, you can see that, right? Yeah, okay. The reason you can hear me saying ah versus e, even if you don't see me, is that these bands of frequencies called formants form, okay? So for ah, the two bands of frequencies are very close together. For e, the bands of frequencies are far apart. Now, do whales do something similar? On the surface, no. If you only look at these clicks, they sound like clicks. But our AI model told us, no, there's also spectral properties that are meaningful. So we had to say, okay, maybe we have our timing wrong. And actually, when you start, so these clicks are relatively far apart, right? Click, 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 click. And our vocal folds vibration. Okay, the way we produce vowels is our vocal fold vibrate, and I change the shape of my vocal tract. Our vocal tract fold vibrates very quickly, right? So you see in the human vowel that the flaps go up and down very quickly. In sperm whales, they go very slowly. But when you start making them more human-like in a sense, when you start removing the timing, these spectral properties that are very similar to human vowels start appearing, okay? So we needed to have that extra step to remove timing, and then these beautiful vocalic patterns started appearing. And this is one example, right? So if you take codas, remove timing from them, you basically get discrete types of codas that are only dependent on the spectrum that we didn't know before existed. Okay, and so for example, you have a set of codas with two peaks that we call the I vowel, and a set of coda with one peak, and it's fully discrete. They never interchange. It's not we didn't even cluster this. Reviewers are angry that we didn't cluster, but this is a pattern so clear that you don't need any clustering. You can basically take a piece of pen and transcribe the two types. It's either two peaks or one peak, and they exchange that in conversation. And you can even hear it. So first you can hear the difference between the two? Okay. And so they have a set of these vowels that they exchange. And if you remove timing and you just listen to what you're going to hear, it's just a set of conversation where we remove timing to make these codas more audible to us. and you can hear the different types interchanged. Okay, so this is making the communication system more like, so that we can perceive it more. We also observe other types of patterns that are probably controlled, where something we call diphthongs, where one of the vowel types the spectral means can go up and down. Okay, so you can see these patterns where you have this kind of nice spectral means, or they're kind of going up. We have one set of patterns that are very interesting, where the first click has very high spectral mean, and then the rest is either level or slightly rising. So, and then you see in the last one is this extreme case where, spectral, I code it by now, gene, where spectral means go really fast up. So what was considered to be just an exchange of the same 1 + 1 + 3 coda type, click, 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 among whales, is actually now an exchange of also these vowel types. And if we look at how this was produced, it's even more similar to human vowels than we thought. So we went and checked at their anatomy, and the way we produce vowels is we flap our vocal folds, right? And each flap of the vocal fold is an equivalent of a click in whales. But our vocal folds, of course, flap much faster. And on top of that, we have this resonant body that is our vocal tract, which shape we change. So we get A and E. And sperm whales, in a seemingly convergent evolution, because these phonic clips don't have equivalents, direct equivalents in our vocal folds, they develop these phonic clips with which they click. And on top of those phonic clips, they have the so-called air sac, a small air sac, whose shape they change to get the spectral property. So you have both the vocal folds and the resonant body, and they have phonic clips and the resonant body, and they seem to communicate with that. And the interesting part was that there was a period where our model predicted these. It predicted spectral properties and spectral regularities is meaningful, and we didn't know that yet. And then we went and checked. We needed that extra step where we needed to conceptualize their time in a less human way, but we were able to find these patterns. Now, AI interpretability, I think, so combining these models, and these need to be pretty much handcrafted models, but combining them with an introspection into these models can give us really important insight in science. But of course, humans in the loop are still necessary. And just to conclude, I think it's exciting time because we have the humans now, we have the animals, we've had them for a while, and now we are adding a whole new intelligence into the picture. And I think we are mutually informative. I think we can use AI to understand animals, we can use animals to understand humans and animals to understand AI. So I think it's just this wonderful tripartite world. And I think it's very important that we make progress in understanding how these models work, how we learn, and how we're similar and different from each other, and how we can use AI to our advantage. All right, with that, I thank you for your attention.
One question for lunch.
Well, and also a quick announcement, I was wrong. The seminar is not in this room, so relax and you can eat in this room.
Okay. Question?
What about the perception? Because you could have reached the same conclusion with the.
Well, we are able to show that they can perceive these vowels as well. At least physically they can perceive. I mean, and in hearing it's also perceivable. But what we have is a whale who was tagged, who wore a microphone, and another whale who was vocalizing. And on that other vocalization from the other whale on this tag, you can also get the vowels from. So it at least is perceptible, and it's within the range that it hear for sure.
You remove time, but like, what if you do a space-time transformation? Are they using both axes?
Probably. Yeah, that's something but we remove time in order to show there is a
Right,
pattern.
understand.
The obvious next step, what are they saying to one another? How does this, well, a couple of things there. Obviously, one of them is the behavioral, I'm doing this, I'm just signaling I'm going down. I'm doing this, I'm signaling I'm going to, just go to sleep now, whatever. But is there any reason to believe whatsoever they're actually engaged in a discussion?
Well, so the way they have dialogues is extremely interesting. They kind of match the timing. Sometimes they have overlapping codas, sometimes they don't. So it's very elaborate. So that's one thing. I'll just say two things because this is nice. I've learned a lot today. Their worlds are so different that it's very difficult to make intervention or even represent their worlds. So that's a difficulty with whales. On the other hand, primates and prairie dogs and other animals have, in a sense, more gestures and extra sound communication that they could use. I think the nice thing is with whales is that if there is information exchange, most of it is probably in the acoustics.
Vin, what's your question?
So
Oh, I guess he's dropped. I just asked because
That was a legacy hand, sorry.
I just asked because you always have a question.
I know, this time I don't.
Okay.
any way that you managed to actually take these vowels? Well, first of all, obviously, is there an analog of our consonants, which is the distinct ways we chop off vowels? But also, did you manage to actually do some kind of clustering over time to actually identify distinct words?
That's next step, yeah. So how they're ordered, what's the properties of ordering, or that's very exciting. Yeah, we already see some of. So like we have diphthongs are more common on long vowels in human speech. Diphthongs in their codas are usually on codas with multiple clicks and parallels like that. So working on it.
Okay, so it's lunchtime. We restart at 1:30 and help everybody by being here at 1:30 so we can start then. Thank you all.